Okay, so we spent Tuesday talking about basically the breakdown of carbohydrates so we can produce energy. So with this one, we're going to talk about fats, and we're going to mention proteins at the very, very end, but we're not going to really get into them. So most of this is going to be spent on fat. All right, and so here are our objectives for this short lecture. So when it comes to fat, we store a lot of it, right? Glycogen stores, we have about 2,500 kilocalories. That'll get an average human through a day. That will not get me through a day. At least according to my Apple Watch, I use about 4,000 calories a day. So good thing that there's more than just glycogen. All right. When it comes to fat, your body stores about 70,000 plus kilocalories. Okay. So again, if we go back to the typical human, that's like 30 days worth of energy. Not quite that much, but you get the idea. Okay, so really, if you think about it, unless you're in a starvation state, you've got an unlimited supply of energy. So as I mentioned before, there's a lot of different types of fats, but when it comes down to it, we're really utilizing the triglycerides to produce ATP. And fat is stored in muscle fibers, and it's in adipose tissue, right? So you see this when you eat protein, right? When you eat meat. So you've got one of the things that makes a good steak good is how much marbling there is, right? So that's why a lot of people prefer ribeye over to other cuts. That's why I don't really like filet mignon, because there's no fat in it. And it's very tender, but there's not a lot of flavor. And I apologize if any of you are vegetarian, okay? But you can see that, and then obviously there's fat tissue as well. So a triglyceride, as we mentioned before, we need to break it down to use it. And so we've got 3 fatty acids, and you'll see the acronym FFA, and then a glycerol molecule. Now, in order for us to use these, we have to convert them to acetyl-CoA. So this is kind of the same process as what happens with pyruvate. In order for us to take advantage of pyruvate and get the most bang for our buck out of a glucose molecule, we have to convert those pyruvate molecules into acetyl-CoA. And so this whole process is known as beta-oxidation. All right, so to start off, we have to get the fatty acids prepared, so it costs 2 ATP to get them ready so we can break them down. And then what happens is we take these fatty acid chains, and what they really are is a string of carbon chains, or a string of carbons. Okay, and so we break off pairs of carbons. And so for each pair of carbons, we produce 1 acetyl-CoA. So for example, like it says here, if I've got a 16-chain carbon, then I can produce 8 2-carbon chains, which means I will ultimately be able to create 8 acetyl-CoA molecules. All right, and so when we break these chains down, we actually are also forming NADH and FADH2. Now, where do you think that's going to go? Well, those obviously are going to go into, or maybe not obviously, but those are going to be used in the electron transport chain, which we talked about last time. Now, in order to break a 16-carbon chain into 8 pairs of carbons, that only requires 7 cuts, right? So as a result, we break this down, and now we've produced, so far, we've got 8 acetyl-CoA molecules, we've got 7 NADH molecules, and 7 FADH2 molecules. Okay. Now, fatty acids can be all different lengths. Generally, they're anywhere from 14 to 24. So we're just using 16. I believe it's palmitic acid. It's a fairly common one. So this is just an example. And just to be clear, I will never have you calculate, well, how many ATP are produced from a 16-chain carbon as opposed to a 24-chain carbon. Not important. I don't need you to do the math. It would take too long, that sort of thing. But we're going to go through this example as if we had a 16-chain carbon. So, like we said at the beginning, it costs us 2 ATP to liberate those fatty acids. All right. And we've got FADH and FADH2 and NADH floating around, as well as the acetyl-CoAs. These go through electron transport in Krebs just like they do with carbs. Okay, so one turn of the Krebs cycle produces some ATP, some NADH, some FADH2. Okay, so going back to our 16-chain example, at the beginning, it costs us 2 ATP. So at the very beginning, we're down 2. It's kind of like glycolysis. We spend 2 at the beginning. So with beta-oxidation, so we're breaking down these these fatty acid chains into their individual pairs of carbons, we end up with 8 acetyl-CoA, 7 NADH, 7 FADH2s. Now, I want to make clear that this is a single fatty acid. Okay, remember, triglycerides have 3 fatty acids, so we're just talking about what happens when we break down one fatty acid. Okay, so we can take each of these acetyl-CoAs and put them in the Krebs cycle. That produces 8 ATP. We get rid of these acetyl-CoA. Each turn produces 3 NADH, so 8 times 3 is 24. 8 times 1 is 8, so we've got 24 NADH and 8 FADH2s. And then what happens is we take those 31 NADHs and those 15 NADH2s, and we end up with 100 ATP. We produce 100 ATP from there. And so ultimately what happens is a single 16-chain fatty acid will produce 106 ATP. Okay, so that's 3 times. So one fatty acid is produces 3 times as much ATP as one glucose. Okay, and if you wanted to go one step further, one triglyceride molecule, if it's made up of 16 chain free fatty acids, 3 of them, then we're getting closer to 9 to 10 times as much ATP from a single triglyceride compared to a single glucose molecule. Okay, so there's a much greater capacity for energy formation here. Okay, the problem, and I put problem kind of in air quotes here, it's not really a problem, but one of the things to consider when we're using fat is that to break down fat, it takes longer, it requires more oxygen than it does with glucose. So I want to end real quick by talking about proteins. As mentioned earlier, we don't use proteins very often for energy, but these proteins are composed of those amino acids, and these are chains that have nitrogen on them. But we can use them as fuel if we convert them into glucose. So example, again, this is gluconeogenesis. We can also just convert them to pyruvate or acetyl-CoA. When we do this, the energy yield is similar to glucose. Remember, 1 gram of carbs gives us 4 kilocalories. 1 gram of protein gives us 4 kilocalories. And so that's where we're going to end.